Thank you, Mike, and thanks again for inviting me to speak in this very nice seminar. So I'm going to speak about some recent joint work with Youness Lamzouri and Jared Lichtman on what we call the Erdős dilation approximation problem. Yes. Okay. So what is this problem? So we're given a set of real numbers A, and the question is how large should A be so that we can guarantee solutions to the inequality alpha minus n times beta less than epsilon. So alpha and beta are distinct elements of our set A, and n is an integer. So we want to approximate an element of our set alpha by a dilate of another set of our another element of our set A. We want this to be as good as possible. And okay, just some very trivial remarks to get us started. The first one is if I assume that the distances between the elements of A get as small as possible, then phi is 0, then of course I can just take n to be 1. There's not much context to this question. And therefore I will be implicitly assuming throughout the talk that the set A is well spaced. Let's say there is some constant delta such that all the distances between different elements is at least delta. So it's like a discrete set. In particular, it's countable. Okay, so towards this problem, Erdős conjectured in the 40s that this inequality star indeed has solutions with A and alpha beta distinct and n an integer. And we can always guarantee solutions as long as the lim sup, so the upper log density of A is positive. So he asked this question in many forms. This was one of the forms originally asked. He also asked if we can replace this condition here with the upper log density being positive by this weaker condition that the sum of 1 over alpha log alpha diverges. And this question appeared many times during Erdős's lifetime. He had all these papers with various problems he liked, so he mentioned it many times. In this form, and also in a joint paper with Sarkozy and Zemeredi in 68, they asked a weaker version of this question, whether we can solve this inequality here when A has positive lower regular density. Let's have at least constant times x elements of A up to x. Okay, so this is the question. And a nice quote, a funny fact about this question is that Erdős, towards the end of his life, he offered a prize, one of the Erdős prizes for this question, $500. But the way he phrased it, it was quite funny. He said, "I offer $500 for settling this annoying Diophantine problem." Well, we saw that we were quite amused. Okay, so right. So what was known about this question prior to our work? So I'll start not in the direct chronological order because it's a bit more natural to start with a result proven later by Haight in 1988. So if you view this as a sort of like Diophantine approximation question, it should be a natural first step is to understand this question when the elements of A don't have linear relations between them. And in particular, the simplest one would be to look at ratios, alpha over beta. And if all of these ratios happen to be irrationals, for distinct alpha and beta, of course, and then Haight proved Erdős's conjecture. In fact, he proved it in an even stronger form, where he assumed he only needed to assume that the upper regular density of A is positive, which is weaker than asking the upper log density to be positive. This is just some small technicality, but nevertheless, he proved under this hypothesis, when all the ratios alpha over beta are irrational, that Erdős's conjecture is true, meaning that we can always solve this inequality with alpha and beta distinct and n natural number. Okay, so I'm going to explain now the main ideas in Haight's proof because they're going to play an important role in the later in the talk. So what Haight does is a second moment. He uses a second moment method. It's a clever argument. So what he does is to consider these sets H alpha. For each alpha in our set A, I'm going to consider the set H alpha. What is this? For every, I take all the dilates of alpha and then I put an interval of diameter epsilon around them. And we're gonna work then in a fixed compact interval 0 up to capital T, where capital T is just some large parameter that will tend to infinity. And I'm gonna write probability sub P sub T H of alpha. This is like the relative density of H alpha contained in this compact interval. So the measure of H alpha in this interval. And it's very easy to see that this is about epsilon over alpha. Okay. Now, the second observation of Haight is that if there happen to be no if I take any subset I like, my favorite subset A prime of A, uh, and then I look at all for every beta now in the complement of A prime, I put an interval of diameter epsilon around it. And then if there are no solutions to this inequality, all of these intervals will lie in the complement of H alpha, because otherwise they would just be a solution. So using this now can take measures and compare the two sides, and then this gives me, of course, the measure of the left-hand side is epsilon times the cardinality of A minus A prime. So if I can get an upper bound on the right hand, on the measure of the right-hand side as well, then I have an upper bound on the side of A. Okay, so in order to get an upper bound on the right-hand side, on the measure of the right-hand side, we need to show that this union gets very large. So it's covering all of the real line. And this is where the second moment method will kick in. So the second is exactly suited for this kind of questions where you want to show that the union of some set of sets is large. And then what you want to do is to compare the first moment. So you just sum the probabilities or the measures of the sets and you compare it to what you get with the pairwise intersections. And if it happens that the pairwise intersections, after we normalize, so this I view this as a probability, if it happens that the probability of the pairwise intersection is roughly the product of the probabilities of the individual sets, then by Cauchy-Schwarz we get that basically this measure is very large of the union, as large as it could be. And Haight, using some basic Fourier analysis, showed that as long as the ratio alpha 1 over alpha 2 is an irrational, and then you take t to be huge compared to alpha 1 and alpha 2, then you have this estimate. It's not so hard to show this using basic Fourier analysis. And then the second moment method tells you immediately that, well, if you're assuming that all the ratios are irrational, that this union has very large measure. So the probability that we're in this union is basically 1. Therefore, the probability that we're in this union, in the complement of this union is basically 0. And as a consequence, the left-hand side must have very small measure, which translates to A having very few elements up to T, as T tends to infinity. So this is Haight's proof in a nutshell, and we'll use it again later on. Okay, so this is what Haight did in the 80s, and sort of the complete opposite of Haight's setup is what was considered by Erdős and Behrend in the 30s. So this is actually the motivation of why Erdős asked this question. He was studying what we call primitive sets of integers, and this is how he arrived at this more general question. So Right. So what we have here, so we have a set of integers a, and in this case, if I fix some epsilon to be between 0 and 1, then this inequality, alpha minus n beta being less than epsilon, is actually equivalent to having exactly to alpha being a multiple of beta. And these are integers, so this just means that beta divides alpha. And now the contrapositive, the absence. So when a set has no such solutions, so if there are no distinct elements alpha and beta in a set of integers such that alpha divides beta, then we say that A is a primitive set of integers. And these kind of sets were studied a lot in the 30s by Erdős in particular. And Erdős proved that if A is primitive, then the sum of 1 over A log A, 1 over alpha log alpha, converges. And Behrend in 1935, so the same year, he proved that if A is primitive, then he proved a quantitative bound for the log density, how large it can get. So he proved that it gets at most log A over square root log x. Sorry, log x over square root log x. And this upper bound is actually sharp. You can construct quite easily examples that basically attain this up to order of magnitude, and there is even literature where the constant here is specified. And okay, so if you take a set of integers up to x, such that they have precisely log x prime factors, then this forms a primitive set of integers, and this has precisely this kind of density. So this would be Behrend's result, upper bound being precisely best possible. And I mention this because this is gonna be Chekhov's gun. Okay, so just for historical reasons, I also like to mention this result of Besicovitch. So starting from the trivial observation that the set of integers in a dyadic interval y to y is primitive, just because if I multiply an integer by 2 or 3, I always fall outside of this interval. Then using this, Besicovitch constructed an infinite primitive set A, such that the lim sup of the natural density is 1/2. Okay, so even though Behrend tells you that, and Erdős tells you that primitive sets are sparse, they actually can get quite dense sometimes, so that the natural density gets positive, even though the log density is 0. Okay. Right. So, and again, because it's going to be very important for what I'm going to mention later on, I would like to explain a little bit Erdős's proof. Right. So, how Erdős proves his result about the convergence of 1 over alpha log alpha. So, he starts for every alpha in our set. He says, I'm going to consider the set of multiples of this integer and alpha, but I will only take n, the dilates, to be alpha raf. Alpha raf means that all of the prime factors of n are bigger than alpha. And then using some very big basic sieve estimate, we can show that the number of elements of E alpha between 1 and x is about x over alpha log alpha. Okay? But then Erdős observes that if our set A is primitive, then these sets are actually pairwise disjoint. Okay, so it's actually a very simple proof. So assume that you have an intersection between these two sets, and let's say alpha is greater than beta for the sake of simplicity. Okay, so we have m alpha being n beta for some m being alpha raf and for some m being beta raf. And alpha here is bigger than beta. So if I compare here the alpha raf, these integers are the same, so their alpha raf parts are equal, meaning the parts composed of primes bigger than alpha. And on the one hand, the alpha raf part of m alpha is m. And on the other hand, the alpha raf of m beta is whatever is the alpha raf part of n, because all the prime factors of beta are less than beta, which is less than alpha. So if n is the alpha raf part of n, then in particular, m must divide n. And if you look at this, if m divides n, then beta must divide alpha. And this is illegal if we have a primitive set of integers and alpha and beta are distinct. So that proves what I claimed in the before, that these sets E alpha actually are disjoint if A is a primitive set of integers. And then we just do a first moment kind of argument. We just sum the cardinalities of these sets, and we know that they're all disjoint and they're all like between 1 and x. So therefore, the sum of the cardinalities is at most x on the one hand, but on the other hand, we know they're like x over alpha log alpha by the sieve. So if I clear x from both left and right, here I get a convergence, the convergence of 1 over alpha log alpha. Okay. So this is pretty much when the problem stood since Haight. So this was Erdős in the 30s. He did this and Behrend, and then Haight in the 80s. But then there was not much more known about the problem till recently. Right. So together, so like I said, together with Youness, Lamzouri, and Duke and Lichtman, we now have proof in full generality of Erdős's conjecture, at least in the form about the upper log density. So we can prove that if we have a countable set of integers with upper log density, that for every epsilon we can find infinitely many triplets alpha, beta, n with alpha and beta distinct, such that n times alpha is epsilon close to beta. Okay, and that's just a small remark that infinitely many triplets, it's very easy to go from 1 to infinitely many, just iteratively apply a result where you just find 1. So that's just a bit neater to state it with infinitely many. Okay, and right, so how do we in the remainder of the proof, I would like to explain a little bit some of the ideas that go into the proof of this theorem. And in a nutshell, this is one instance of this kind of philosophy called structure versus randomness. And this is why also I presented the proofs of Haight and Erdős earlier. So I view Haight as kind of the random case where you have no structure, all the sets of, like, so if you just randomly choose alphas, they're not going to have any rational relationship between them. So that's the random case. And if your A is maybe like sufficiently random, then maybe something like Haight's argument will still work. So then if it doesn't work, it means there's going to be some hidden structure inside A that if one can find it, then maybe one can use the arguments about primitive sets of integers from going back to Erdős and Behrend to then deal with the structured component of A and then get the savings using this structure. So in a nutshell, this is how we go about proving this theorem. And now let me get down to more specific details. Okay, so let me start with some pretty simple observations. So the first one is that we can, without loss of generality, just work with the case epsilon is 1, just to lighten a bit the notation. That's just, right, if I can solve this inequality for some, right, I just need to divide everything alpha and beta by epsilon and consider the set A over epsilon, which will still have positive log density, and then just try to solve the inequality with 1 here instead of epsilon. Okay, so I will just be assuming that epsilon is 1. Okay, so then again, like in Haight's work, and basically like Erdős and Behrend, we will working in the contrapositive direction. So we assume for contradiction that we have a large set in the sense that it has positive log density, upper log density, and yet for all distinct alpha and beta in A and for all possible integers n, we have that n alpha minus beta is at least 1 away from, right? And alpha and beta are at least 1 far away. And just a trivial remark is that this, if I take n to be 1, this means that alpha minus beta is at least 1, which means that my set alpha is one spaced. Okay, so I have, it means that up to x, I can have at most x elements of my set. It sort of looks like the integers from this point of view. But of course, it could be much more random. Okay, and this kind of condition that we're assuming that the upper log density is positive is actually equivalent to a seemingly slightly stronger condition, but it's equivalent to it, that I can make my alphas basically be within a power of x. So I can find, so if this condition, the upper log density is positive, then it means that I can find infinitely many values of x growing to infinity, such that the interval between x to the eta and x, the sum of 1 over alpha in this interval is at least log x. And I guess eta here is some absolute constant that only depends on my set A. And if you often here, I really mean that x goes to infinity. Right. Okay, so this is the main setup. So we now have a one-space set that is trying to avoid all the dilates of alpha, avoiding elements of the set. And we have many, many chunks of the set where you have, it's quite dense, logarithmically dense. And we want to arrive at a contradiction. Okay, right. So I'm gonna, since already we have a proof, maybe we should just try to just see if, an argument by Haight, maybe we should just see what this gives. So let me recall Haight's argument. So we have this H alpha, which are the unions of these intervals of the dilates of alpha, and then we put an interval of diameter 1 around these dilates. Then we can compute what's the proportion of these sets contained between 0 and t, and it's about 1 over alpha. And we're going to be using the second order method, so we better make sure that the sum of probabilities is large, so that we have a chance of covering the entire interval 0t. And indeed, in this case, because of the first condition here, that the sum 1 over alpha is pretty big, then the sum of probabilities is also pretty big. Okay, so now let us assume there are no solutions to our set, to this inequality, and alpha minus beta less than 1. And just like Haight observed, we're going to then have that this set, this, if I look at beta minus a half, beta plus a half, all of these intervals are going to be completely disjoint by H alpha. So it would then suffice to show that this union has large measure. And again, we're going to be looking at pairwise intersections. And for the second moment to succeed, what we actually need is, on average, the pairwise intersection to behave as if the sets were sort of independent of each other or uncorrelated. But actually, we just need an upper bound. So we only need to make sure that they are not positively correlated on average, which is weaker and it's very convenient when you actually try to prove things. Okay. But it turns out that, so here we're trying to prove the general version of the theorem where alpha and beta can be anything. Well, Haight's argument worked beautifully when alpha over beta was an irrational number. And now let's see what happens in the worst case scenario when alpha and beta are actually integers, both of them. And then it's very easy to compute what this probability is. And it turns out that this probability, H alpha, the probability of the intersection is, well, the product of the probabilities times the GCD of alpha and beta. Okay, and this is pretty bad because the GCD is not going to be 1 all the time unless we're very, very lucky. And in fact, it's much, much worse than that, the situation, because if you sum over if you look at the average of the GCD over typical values of alpha and beta, then the GCD actually grows like a power of log of x. So it's really, really bad, the situation. If we just try to directly use Haight's approach. And this is just when you try to do integers, sets of integers. And you might think, okay, maybe if I do like rationals that have maybe larger denominators, maybe things are going to start working. So um, well, let's try to identify what's the actual enemy here and where this why this intersection might get very large. Okay, so we have alpha greater than beta here, and let's assume we have a rational number because otherwise we know what happens. And let's write this in reduced form, excuse me, as S over T. So S and T are integers here that are co-prime to each other. And when you try to understand intersections between H alpha and H beta, you will always have to deal with the trivial solutions, like the diagonals, where you have that M alpha is N beta for some different MLN. So you always have to account for these solutions. And you better make sure that these solutions are not too large to kill you, to kill the second order method from working. So let's try to understand what this uh, count is, and it's just a simple exercise in elementary number theory to show that this is actually approximately equal to the product of the probabilities for H alpha and H beta times a certain factor alpha over S. Okay, and this factor is very, very important. It plays a very, very important role in our proof, and we give it a name. Actually, we work with the inverse of this factor, which we call the bracket of alpha and beta. So the definition of the bracket of alpha and beta is the height of the ratio of alpha over beta. So height as a rational, like remember you have a rational, you reduce it and you check what's the largest numerator or denominator, that's the height. And you divide by the maximum between alpha and beta. Okay, so this actually equals S over alpha, which is exactly the inverse of this. And so if this bracket alpha over beta is strictly less than 1, then you're going to have a problem here. The second moment method is not going to work. So we actually need to make sure that alpha over beta, we're only dealing with alpha and beta with bracket bigger than 1 to guarantee that we avoid positive correlations that are going to prohibit the second mode from working. And okay, so just like in the integer case, it's not possible to always guarantee this. So if we want a general result for any A, then we're just stuck. But here, Erdős comes to save us. And so here's the solution. Instead of looking at all of the dilates n alpha, then only look at the dilates where n is alpha raf. Because Erdős tells us that for primitive sets, if alpha over for primitive sets of integers, there are no diagonal solutions. These sets are completely disjoint, the sets of dilates. And so maybe this is going to help us. At least we know it helps for integers. Okay, so this is the new definition. We're going to be working with these sets instead of the H with the n alphas. And now we're going to compute. And it turns out that the probability is 1 over alpha log alpha. Okay, this is a bit smaller, but it's still large enough for the first moment to work. Because recall that we're assuming, if I go back, we're assuming that the sum of 1 over alpha is at least log x, but alpha here is between 2 powers of x, so actually the sum of 1 over alpha log alpha is bounded from below by some constant. And I know this infinitely often, so I can take like 1 million chunks like that, and I'm going to have a very large sum of probabilities. Right. So in every kind of this log, this interval x to the eta x, the sum of the probabilities is at least bounded from below. So then if I take many of them that are disjoint, then I'm going to have large sum of probabilities, large first moment, which gives me a chance of covering the entire interval. Okay, so this is not a problem. The fact that we have reduced measure. And this is the key fact that is going to save us, is going to give this a chance of working. It is a simple fact to show that if the bracket of alpha and beta is less than 1, and there is alpha is not the dilate of beta and beta is not the dilate of alpha, then these new sets are actually completely disjoint. So actually, it's actually zero, the probability of them occurring. And this is very good for us because we just want an upper bound of the probability. And certainly zero is a good enough upper bound. Okay, so this is the key, one of the key ideas to use these neighborhoods instead of these events instead of heights, because this guarantees they're less correlated with each other, and we have a chance of making the second one working. Okay, right. So this is our setup. We have this neighborhood, this sets, these events, and we call this key bracket thinking that it controls. It's gonna control how correlated an alpha and beta are. And there is a technical step in the proof that is an important one because it really simplifies it. Okay, so what's the step here? Using Behrend's estimate, or more precisely, a generalization of Behrend's estimate proven by Alsvede, Hachaturian, and Sarkozy, we can now construct by our assumptions that we have lower log density, positive upper log density. We can find various sets of various chunks of our set A that are dense, and they have an additional property that if this bracket alpha and beta is somehow controlled, not by 10 to the beta, or the smallest one, 10 to the smallest one, then this alpha and beta must actually lie in the same chunk. Okay, so it's not possible. So this is going to mean that different the A's for different J's, AI and AJ, are not going to interact with each other unless I is J. Okay, so in practice, what this means is that when you do the second moment, almost all the correlations disappear, and the only things you're going to have to consider are the sort of quasi-diagonal solutions possibilities. Okay, right. So, and why is that? Is because we have we have a sharp correlation upper bound that shows the bound that we want, an upper bound that we want on the probability of these events, and alpha and beta, unless alpha over beta has small height. So, of course, if alpha over beta is an irrational, we know that this is actually asymptotically, the two sets are asymptotically equal. And what we also proved is that if the bracket of alpha and beta is bigger than this threshold, then you still get an upper bound of the right shape. And then if I use this upper bound here, together with this step here, that we can guarantee that alpha and beta being less than 10 to the beta, the bracket of alpha and beta being less than 10 to the beta, only when alpha and beta come from the same chunk, then the second moment, at least for distinct pairs, which is all that matters, can be controlled asymptotically roughly by the square of the first moment, which here by construction has size, that should have been n alpha, not a, sorry, roughly by the square of the first moment, which is like roughly j squared, plus, and then a diagonal term which only has going to have j. So I and j are equal, so I only have j terms now, not j squared. And I'm considering alpha and beta in this from the same AJ, from the same chunk, and I need to understand how the correlation of n alpha and beta. But I have the extra condition here that the height of alpha and beta, the height of alpha and beta is controlled in terms of alpha and beta. And certainly the theorem would follow if we could prove that this here under the brace is big O 1, because then this entire term would just be big O j, which is of smaller order than the main term j squared, which is all we need for the second moment to work. Okay, so now the goal becomes to look at this kind of correlation estimate for alpha and beta in AJ, for coming from the same chunk, having roughly the same log size, and such that the height of the ratio is controlled. And can we control this size? So this is where we need to find our structure, and this is the hard part of this is somehow the heart of the proof now. Right. Okay, so here I've simplified a little bit. So I just rewrote what I just said, sorry. We need to prove this kind of upper bound. And if this factor perfectly, then we would just have this upper bound trivially. And what we can actually show, and this is more or less sharp, we can show this kind of upper bound. So if alpha over beta is S over T, written in reduced form, rational, okay, so then using an upper bound sieve, we can show that this probability of this intersection is controlled by the product of the probabilities times a certain Euler product, running over prime factors of ST. So only prime factors have cleared common factors here, and only prime factors being bigger than the bracket alpha beta. So here you can see a little bit why having large bracket alpha beta is important. Makes the problem somehow easier, because having large bracket is going to make this product having less terms and therefore being less likely to be large. But even if alpha over beta, if the bracket of alpha and beta is equal to 1, so you have the full product here. If you think statistically about this product and think of S and T as being sort of normal integers, then this product should just be at most a constant. This follows by pretty classical things about how the Euler function, let's say, is distributed. Okay, so here is now a revised goal given this upper bound sieve estimate, and I'm simplifying here. And I'm just taking whatever this cutoff here is be x. And then I'm just replacing this maximum alpha beta just by x. Okay, so we have alpha and beta between 1 and x. They're weighted logarithmically by 1 over alpha over beta. We know that the height of the ratio is at most x to the x cubed. And we want to show that this quantity here, the Euler product 1 plus 1 over p over divisors of st, is on average bounded. Okay, so if I didn't have this product, if you imagine this product wasn't here, because our set, remember I said is one spaced, okay, from a long time ago. I said that the set is one spaced, and therefore if I didn't have this factor here, I would just get the trivial bound log x squared. So I just need to show that when I add this factor, on average it's bounded, so I still have the trivial bound. Okay, and if you're an expert in metric Diophantine approximation, you might recognize the relevance here of another problem that requires a very similar looking bound, and this is the Duffin Schaeffer conjecture for metric Diophantine approximation. So this kind of upper bound is very analogous to what was needed to prove the Duffin Schaeffer conjecture. And why is that? Because if you have alpha and beta to be rational, both of them being rationals, let's assume for simplicity that alpha and beta are rationals, which is already hard enough and was certainly open for general rational numbers. So if you have rationals a over q and b over r, then you can work out what this bracket actually means. And it means it's exactly equal to q times r over the GCD of AB and GCD QR. Okay, so then you have an Euler product here that is controlled by the size of GCDs, of pairwise GCDs. You have bilinear sum, so you have pairwise GCDs that sort of control how large this product is, together with some sort of anatomical information about the integers that are involved here. Anatomical meaning how the prime factors are distributed. Right. So if I rework this a little bit, I'm skipping some steps here, simplify. But then basically you can then simplify this and reduce it to the following question. Okay. So you have here rationals, alpha, beta, coming from the set A. Let's say they have some control height, which is still some power of x at most, x to the 6, let's say. You can actually prove something like that. And let's say that they all have fixed bracket size, m, which is essentially fixing the size of their GCDs. And let's assume that you have some sort of knowledge about how their prime factors are distributed, how they affect the Euler product. And the kind of condition you would be assuming is this one, sorry. That the sum of primes dividing ST after clearing the common factors, prime factors that are bigger than m, summing the reciprocals of those is bigger than 1. And if I just look at this very last condition, for typical integers, this condition occurs with probability something like 1 over e to the e to the m or something like that. So it's a very, very rare condition. And and here we're just asking to save just a little bit, just a factor of n. We don't even care about the exponential. But of course, the problem is that we know nothing about alpha and beta. For all we know, this could be that we don't know how these denominators, where the numerators are, where the denominators are, they could be quite irregular. Right. Notice that we only control, right, so yeah. Sorry, I've only simplified a little bit here. Yeah, sorry. Yeah, so let me simplify a bit further the situation to sort of highlight some of the difficulties that we have here. So for simplicity, I will assume that somehow we're in the case where all the denominators were fixed to be some large integer q. Okay, q could be a function of x. Think of q as being maybe log x or e to the square root log x or something like that. Okay, so we'll have fixed some q, and then we have fractions of the form a over q, and then if I work out this bracket expression between a and b, I find that this actually equals q over the GCD of a and b. It simplifies quite a bit. And therefore, what does this condition mean? That the bracket of alpha beta being of size m, it means that the GCD of a and b is of size q over m. Okay. So now here is the problem is a bit more down to earth because we have sets of integers a and b up to, let's say, x to the 12 that have pairwise large GCDs of size about q over this parameter capital M, and such that they satisfy, once we remove common factors, they satisfy this anatomical condition here. Right? So here's the problem. Now, the trivial bound here would be just log x if I just sum over all a and b up to x to the 12. So the anatomical condition here could indeed gain me a factor of m or maybe even e to the m or something like that. But this is going to be pretty useless if m is very, very small compared to q, because I really need to gain also this q. And where is this q coming from? Because alpha is a over q. So when I replace a over q here, beta by b over q, I get the q squared in the numerator, which I have moved on the other side here. Okay? So we really need to show that it's actually somehow we will say proportion q for a and b. And this is going to be saved by the structural condition that the GCD of A and B is large, of size q over n. Right? So why do I call this a structural condition? Because a very easy way to guarantee large GCDs is if somehow all the sets A and B, all the integers A and B that I'm considering here, had a fixed divisor of size q over n. Then, of course, all the pairwise GCD would be large. So this would be a case we would have to consider. However, for this case, it's quite easy to show this kind of bound because you get the q squared by the fixed divisor, and then you lose m squared because it's in the denominator, but then you're gonna gain like e to the m from the anatomical condition. So you're gonna be able to prove this upper bound in this case. Right. So the question is how to actually find this kind of structure. So the structure is going to be locating this fixed divisor. So this is precisely what was needed to be done for the proof of the Duffin Schaeffer conjecture. It's completely analogous. What I'm saying goes back to the proof of the Duffin Schaeffer conjecture, which is joint work with James Maynard. So here is so in order to actually find this fixed divisor, we developed this method that we call the method of GCD graphs. Okay, so what we did was to view this just in the language of graphs because it just made it more convenient to form a graph every time you had a large GCD. And to show that somehow by pruning this graph, you can like focus on a subgraph that is very much structured, where all the vertices, like check a complete graph where all the vertices are forced by just some fixed divisors. So find these divisors and then finally use this anatomical condition to gain back whatever factors of m you need. So that is the strategy. But there is a caveat, a very important caveat, that in the Duffin Schaeffer conjecture, we prove the method we developed with Maynard can indeed prove this, but only if we put some slightly smaller weights, phi of A over A. We multiply this by phi of A over A and then phi of B over B. And this is very, very important. These weights come for free in the Duffin Schaeffer conjecture because they were doing the final approximation with reduced fractions, and that's why the Euler function pops out. But here we don't have them. They're not just built into this problem. So actually, for some time, we did wonder, is Erdős' conjecture false? Maybe one needs to modify it and put this kind of weights in it, which would make it actually very ugly and very complicated to formulate this problem. But actually, it turns out that you don't need this kind of factors because you can like create them somehow. And here's how we do this. So the proof of the Duffin Schaeffer conjecture, what it does basically when you run this algorithm, it iteratively, prime by prime basically, it produces fixed divisors for A and for B. Let's call them capital A and capital B. Not really for A and for B, but somehow like some dense subsets of them. You view this as somehow a bipartite setting where you have on the left A, on the right B, and you connect the vertices, and then you somehow find some smaller subsets of them, and you find some fixed divisors in them, capital A and capital B. But in order to produce these fixed divisors, A and B, capital A and capital B, there is a key loss in the very last step and most important iterative step of the algorithm. And the loss is for every time you iterate and you find a common divisor of capital A and capital B, you end up losing a factor of 1 minus 1 over p squared. And this was okay in the Duffin Schaeffer setting because you have this phi A over A and phi B over B to precisely counterbalance this loss. Like, so you lose this factor, so I should have put a minus 2 here. You have the minus 2, but then you gain it back from the phi A over A twice, once from A and once from B. But here we don't have these factors. Well, it's okay because we could gain these factors by doing a little bit of sieving, if only we knew exact divisibility. So what we would need to do to know in order to gain back these factors is to somehow that knew that after we find this fixed capital A and capital B, once we divide through A by this capital little a by capital A, then what remains is co-prime to capital A. Then when you sum over the remaining part of little a, then just by a little bit of sieving, you recover phi A over A, just because its prime factors are missing by a very simple sieve. But unfortunately, it's fundamental in the proof of the Duffin Schaeffer conjecture that you cannot guarantee this, at least in the version of that we developed with Maynard. And okay, I'm slightly lying here. There is, for example, you could guarantee this kind of thing if you somehow knew that all of the little a's were square free. Okay, for example. Then, of course, once you divide by divisor capital A, what remains is coprime to A. So you have this coprimality, but again, square free does not suffice to prove the full conjecture of Erdős. But fortunately for us, just about a year ago, Hauke, Vasquez, and Walker published an alternative proof of the Duffin Schaeffer conjecture, building on earlier work of Green and Walker. And this work, what it showed is that one doesn't need to do this very last iteration step. So instead, what they did was to stop right before this iteration step where we're losing these factors 1 minus 1 over p. And so if you stop right before this, it's good because then you guarantee exact divisibility that is necessary. The cost you have to pay for this is that you haven't fixed completely the GCDs and the divisors on the left and on the right. But instead, you have to sum over some possibilities for the divisors on the left and on the right. But that's okay because you still have this weights phi A over A, and this actually turned out to be enough in order to counterbalance the extra summation that you're performing. And again, so somehow the magic cancellation that occurred in the first proof with Maynard, in the GCD graph approach, also occurs somehow is in another place in the proof of Hauke, Vasquez, and Walker in their approach. But that's okay for us because what we can guarantee these factors phi A over A using the sieve. So this approach is perfect for us because we can make this work. However, I told you there was going to be a twist. And this argument that I just described only works if you fix Q. But in our case, we don't have this luxury of fixing the denominator Q, and rather we have to work with arbitrary denominators. So what we actually have to do is to use, so the first thing one has to do is to just generalize the method of GCD graphs so that they work for graphs where the vertices are rational numbers, and with the end goal of fixing divisors of numerators and the denominators to explain large GCDs up and down, the numerators and the denominators. And that's really not a big problem. It's a pretty straightforward generalization of what was already done with Maynard. But this leads to a problem when you use the Hauke-Vasquez-Walker argument. It turns out when now you have to sum over all possibilities of GCDs, but up and down. And when you do this, the sum turns out to be too large. So it looks like even this approach now is dead, but magically, there is a little bit more savings that we can exploit. And this comes precisely from the savings built in Behrend's estimate and the generalizations by Al-Suede, Al-Chatrian, and Sarkozy. So what Behrend saves is precisely, Behrend tells you that not only you can save, well, the sieving we know we can save just elementarily, but Behrend tells you can also save square root log x because the integers here a are not just all integers, but they actually come from a set of primitive set of integers. So we got an extra set of savings from Behrend. And this square root log x is precisely the correct amount in order to counterbalance the losses by summing over too many possibilities in the Hauke-Vasquez-Walker approach. And really, if Behrend had any function here tending to infinity, times log x over square root log x, this would not work anymore. So to me, it still remains a mystery how Behrend is exactly what is needed to counterbalance the losses. And the right, and just remember what I said before, that Behrend is actually optimal. It's not that we can expect to improve this and okay, we didn't work hard enough to get a better savings here, so we had actually a lot more room. No, Behrend is actually optimal. You cannot improve the square root of log x factor, and this is precisely the factor to counterbalance the losses from when summing over the possible divisors in the Hauke Vasquez-Walker approach. Okay, so this is what I had to say about the proof, and then let me just conclude with a few open problems for people who might be interested to work on. So let me go back to Erdős's original formulation of the problem. So if you remember, I said that Erdős asked various variants of the problem. One of them asked if you can prove existence of solutions. Sorry, that should have been equals to infinity. Oops, sorry. So if the sum of 1 over alpha log alpha diverges, then can you guarantee you can solve an alpha minus beta less than epsilon? So our method certainly does not prove this. And there are at least two spots, two places on which we crucially use the fact that the stronger condition that we're working with implies this condition that you can focus on intervals that are of fixed log size, where alphas are fixed log size, and you can even assume these intervals are extremely spaced apart, so they don't interact with each other. So we don't have, yeah. So I'll be, I believe this conjecture of Erdős corrected with equals to infinity here, and I do think that proving it requires some genuine new ideas. So that's a very interesting research direction. And the second one, that is a little bit more on the quantitative side, is, for example, let me just look at the setup the simplified setup I was examining before, where you fix Q and you look at an index set A of rationals, but all denominators are equal to Q. And let me write N for the set of numerators. And in this case, what we seek to prove is that NA minus B, right? So we seek to show that if there are no solutions to the inequality, so we assume that we always have the reverse inequality, so NA minus B is greater than Q for all distinct A and B, then the sum of 1 over A is little of log X over Q. So you need to not only win little of log X, but you also need to win this factor of Q as X tends to infinity. And if you actually unpack the proof, our proof, we actually, in this case, we just basically treat this as a case of fixed X and X being fixed Q and X being humongous compared to Q. We need X to be at least e to the Q squared because we just use Behrend's estimate to it. So a very natural question and tangible would be to understand what X is as a function of Q such that this star thing holds. Can you actually prove a quantitative estimate like a la Behrend? Or can you prove something about the sum of 1 over A log A, maybe say 1 over Q there, in an Erdős type estimate? These are all open questions that I think would be quite interesting and natural places to start working on. Okay, so that's all I have to say. Thank you for your attention.